Okay, good morning, everyone, and welcome. This great island of Portopia in Kobe. We appreciate your coming. Also, those of you who are presenting, and also those who are not presenting, but also, of course, inherent a part of our ongoing endeavor towards high-performance computing, either within R-CCS or our various dearest collaborators. It's a great honor to be here and to present to all of you, and also people who are listening from outside. We have this in recording as well as live cast. So what I'd like to talk to you about today is just not only a status quo of where we are, but also where we are going with respect to next generation FugakuNEXT. And but try to keep it under 50 minutes, which is always a hard job to do. So currently this is Fugaku, and there'll be a tool tomorrow. So if you haven't seen it, it'd be good to see it. Even if you have, as I will allude to later, there's a little bit of new additional stuff that might be of minor interest to you. So you may go there anyways. But it is on a machine that's been in operation for the last 4 years to produce great scientific results. And also the center has grown quite considerably. And actually, I'll show you that it's going to grow even further, starting next April 25. But we have lots of very capable leaders, as well as we're recruiting very aggressively many researchers. So those of you who might want to have not only, of course, want to come work for us, that's fantastic, but also we accept many visiting scholars, and also people with joint affiliations. So in fact, some of these team leaders, or now we will call them team principals from April, some of them do have affiliations in other institutions. And also, some of the researchers may have affiliations, even with foreign institutions. So again, you're very welcome. If you would like, you're very welcome to try to knock on the door and try to join our family. So I won't really go into. I don't have time too much to talk about Fugaku's achievement as much as I would like to, but as we all know, it has achieved not only premier spots and synthetic benchmarks, but also it's been very effective in producing real impactful scientific results, such as the Golden Bell Prize winning COVID research in aerosol dispersion in resolutions and accuracy never seen before. And also in the 2025 Expo in Osaka, we will have the upgraded version of the Tokyo Olympics real-time weather simulation done by the team led by Takema Sumiyoshi and Hirofumi Tomita to do a live cast of very accurate forecast of the weather and temperature and so forth at the Expo by combining inputs from multiple phase array radars and doing data assimilation real time. Using about a little bit close to 1/10 of Fugaku continuously, and then do the live cast of the results to respective people attending the expo, their personalized weather information. So we can do things like that. So the assessment of the impact of Fugaku, what's the ROI? Has been significant. We worked with Hyperion, which is one of the two premier international consulting firms regarding HPC to assess the ROI and other impacts of Fugaku. And Hyperion in 2023 report came to the conclusion that Fugaku's impact is almost 68 to 90 times its cost, which is sort of hard to believe, but still very, very. We were very surprised by this. So this translates to like 100 billion to 135 billion. And now we're working with them on the 2025 report with addition of AI elements. We expect to have ROI of more than 100x. So this means that the investment that the governments are making with respect to HPC is not only impactful in AI, as has been with the most recent hyperscaling making commitments to these enormous investments in their infrastructure, but also, it's in the non-AI elements are also very impactful. So both combined will bring about significant contributions to society, and that's why it's very important that these investments are continued. And it's not just about the machine, as we'll allude to later, but it's about all the way down from the facility, and of course to the machines themselves and the evolutions thereof, but also algorithm software, the interfaces, and of course the many applications and sciences that will be that are groundbreaking sciences that will be done on the system. So where do we go from here? Well, this is sort of similar slide to what I said yesterday, but just to tell you that many of these research and development have been approved and also have been enhanced or have already yielding good results. So Fugaku, we're making lots of improvements on Fugaku to continue its operation to about up to 2031, or it could be beyond, in fact. So one reason is while we're putting up FugakuNEXT, we don't want the disruption that was caused the last time when we shut down K. The K computer and Fugaku was not available for about 1.5 years. We want to avoid that situation. But even after the new machine comes up, if Fugaku proves to be valuable, especially for CPU-based applications, then we will have the ability to keep it in operation for a long time, as long as it's deemed feasible. But of course, it does not come for free. There's continuous improvement. Also, there are efforts to disseminate the results of Fugaku to other machines, not just outside machines, but some of the machines will be facilitating. And of course, there's an R&D of FugakuNEXT, which will start to happen at 2025, but now officially been designated, and I'll talk about that later. But the big objective is there are several big objectives, of course, to achieve yet another orders of magnitude improvements in performance. And this translates to going to maybe what may be called a Zettascale age in the 2030s. And of course, we're advancing AI for science, and we're also pushing forward on quantum. But you'll see many of these presentations, but I'll try to give you a context and a framework of how we are thinking about these things. So, firstly about Fugaku. So in 23, we signed an MOU between AWS to do the project, to start a project called Virtual Fugaku. This is this with the realization that many of the supercomputers are now very cloud capable and increasingly so. And of course, we're making progress to make our supercomputers are part of the cloud. But the other direction, putting all the capabilities and outcomes of our research regarding supercomputing into the cloud is also important. And thus, this project, Virtual Fugaku, came about. And in collaboration with AWS, we have succeeded to basically replicate the Fugaku environment entirely in the Amazon cloud in their Graviton processor. But of course, since much of the software is processor agnostic, we can make them available in other environments, such as x86 and other supercomputers. So we just did a release of Virtual Fugaku last summer. This was targeting the AWS Graviton. In reality, right now it's a container that contains the Fugaku's programming and execution environment. So it's not just about the libraries, it contains many of the key software open source or some that we developed, and some of the software that were derived from other projects such as ECP into a container. So it becomes a self-contained execution environment, and will look and feel just like Fugaku. But also got rid of most of software dependencies on Fujitsu. So we are now very much vendor agnostic. And that was one of the hidden names of Virtual Fugaku, that we are in full control of our software destiny, so that we can be quite vendor agnostic when we field new machines or try to design new machines such as the FugakuNEXT, and also allow other proliferation to other cloud as well as other supercomputing environments, and work with other institutions to finally come up with some standardized distribution of a supercomputing environment. And so right now, again, the first version is out. You can download it from GitHub. And this will allow you to create what we call the private Fugaku here. So private Fugaku is the only Fugaku environment. So this it still is fairly nascent. So you have to put up your own virtual cluster in Amazon, in AWS, and load up the containers and so forth. But we're working to make things more turnkey, such that you can just with a single push of a button, basically, to create your own privatized Fugaku environment. We also have satellite Fugaku environment we prepared and are in continuous operations. In fact, if you look at the Fugaku status dashboard now, at the very bottom, you see this Fugaku's certification environment for AWS. This allows our existing Fugaku users to certify their applications that will run on the AWS virtual Fugaku environment. And of course, it's not meant for productions. It's a very small number. Very small number of nodes. But this will allow for people to test their applications such that it will allow them to say this is a virtual Fugaku compatible. So again, this is not only a software stack in itself to emulate Fugaku, but is the basis for fully vendor-independent, ready-made OSS stack for HPC and AI. I'm also working a lot on saving energy, of course, for societal and moral reasons, but also for pragmatic reasons, like we really have to save money because energy prices are getting uber expensive. And also, there are mandates with respect to CO2 emissions. Now we are mandated to power our machine at least by 30% by renewable energy. So, of course, what we do is we don't have solar power like wind towers or solar panels. Well, we do actually, but they're very small. We don't have the capability to generate our own natural carbon neutral energy. So of course we have to buy those from from the power companies. But when we buy those from power companies, they're more expensive. So we have to be very aggressive in terms of thinking about how we would be saving energy, lowering our energy, and also lowering our carbon emission as much as possible. And there are many works in the area. One thing we have been doing is to make Fugaku itself be very power efficient. And this is with the collaboration from the users, not just ourselves, to seek for most efficient power operation mode, given someone's applications. We advise them, and of course we guide them, and we'll try to automate the process. And in fact, right now we're incentivizing people to seek for a power mode that would not sacrifice their execution speed, but still allow to save energy. So they get the same runtime, but they use less energy as a result of setting the appropriate power mode for their applications. Of course, this power modes will depend on the different characteristics of different applications. But again, we hope to automate this process as much as possible using AI methods and so forth in the near future. Right now, this is driven by incentivized schemes, so people will be motivated to seek for the best setting so that they get rewards. So it's a reward-based program. And as you can see, compared to 2021, we started the operation, we have been able to reduce the power requirements of Fugaku per each node by more than 10%. And we can, if we're really aggressive, we can go down to 15% if we would like to. And of course, we're always seeking more and more. And also, we have reduced our operational power requirements by 5%. But again, there are many other things we can do if we have the means and money and time to do so. So we're seeking this as much as possible. All right, switching gears to AI. So AI for science is very important for societal innovation. So Goldman Sachs says that 17.5% of GDP increase will be done by AI, technological breakthrough through AI. But recent Gartner talk said AI will increase GDP by 8 to 9%. But this is not very good, right? This is not what you expect. And this is largely due to the fact that Gartner's analysis was done with respect to just doing, just streamlining your business process to achieve productivity increase. And this is a stark contrast to the actual GDP increase from the 1960s to 2023, which is a factor of 60. So from the time when some of us were born to where we are now, the world is 60 times richer, right? Which is pretty amazing. You can go check for yourself. Okay? Well, maybe not so much in a more advanced country like U.S. or like United States, where things were already advanced. But when you look at the global situation, it's like factor 60. By the way, this kind of corresponds by chance. Right? This is not. There's no correlation there, I guess. But by 60 to 80 times increase in ROI that they have measured for Fugaku. And a lot of these factor 60 increase was achieved by technological innovations and also proliferation through globalization. So AI for science really needs to act to improve science and also its outreach to the society, and both using AI, of course. So we use AI to solve the hardest problems, just as we have been using HPC simulations to solve some of the hardest science problems, and thus achieve societal innovation. We have to use AI to achieve, we would like to use AI to achieve scientific breakthroughs that will advance the GDP by orders of magnitude. And also like to use AI to achieve outreach. So for example, the latter, we are increasingly trying to use AI for the operations, but also user support of Fugaku. So now Fugaku's help desk, and I don't have time to report it today, but Fugaku's help desk is now a chat-based, so driven by advanced RAG and LM combined system, so that now you can converse essentially with Fugaku to get help. Okay, so a lot of these HPC and AI, and also quantum, where this is the result of the collaboration. There will be several talks during the symposium with respect to these collaborations that are happening. In particular, we have signed this. Not us, but the Japanese government has signed this comprehensive MOU between the DOE and Japan and DOE MEXT, Kurihara-san's ministry. I believe this will not change with the current U.S. administration or the current Japanese administration. In fact, hopefully it would be strengthened. And also signing individual institutional MOUs, for example, between Oregon and RIKEN, with respect to advancing AI for science. And of course, we have agreement with various other centers, various other institutions, and we're pushing forward with collaboration globally, US, Europe, and also Asia and other countries. Now, the use of AI science is not a stranger anymore. In fact, many of these teams, in fact, most teams, using Fugaku are looking into or actually are using advanced AI as part of their workflow. So there are many instances, and many of these results have been published to use AI in terms of surrogates, in terms of generating generations of various artifacts, scientific artifacts, such as them been done by AlphaFold, and putting them in the workflow, in a very comprehensive workflow that combines AI and the simulation, such as those in the drug discovery pipeline. So again, these are no strangers. In fact, these are becoming quite the norm for many of the research teams. So, so we have set out to try to survey all this, and then try to see where we should go from here, including the research programs, but also how the machines should be configured and so forth. So we try to create this AI for Science roadmap, and the first version was actually issued about 10 months ago, at the end of May 24. We also have the English translation for the executive summary. And we will try to improve this as it goes along. Probably we'll try to do some work this year to update this, because there's so much changes and advances in AI for Science. But what's been recognized is the fact that AI for Science has a significant impact on many of the in fact, all of the existing computational science domains, from nanoscience to energy, the life science, telemetry, basic science, drug discovery, manufacturing, brain, earthquakes, and weather, climate, etc. Just the whole thing. I don't think there was any exception where the AI, the authors have discovered that AI has no place in the workflow. And thus, RIKEN, as a scientific institution, as a leading scientific institution, as a leading national lab in Japan, and also one of the global leaders, have taken various steps to incorporate AI into the science. So I think the goal was what's called a TRIP project, and one of the flagship projects within TRIP is TRIP Aegis. The goal is to enable AI for Science for all the RIKEN scientists, and then let that proliferate to all the scientists in Japan, of course, globally. So of course, the project, especially the flagship project, TRIP Aegis, aims to have people generate high-quality data and create the data pipeline, so to cleanse and deduplicate and do all that kind of stuff to streamline and standardize the data acquisition and archival process, and then use the data and also things like simulations to have generative models for AI for Science, and then integrate those models into simulations in the high performance platform. So TRIP Aegis is sort of a prototype or trying to demonstrate the effectiveness of the scheme. So we have several teams. We have people developing a common platform. We are mostly responsible for developing some of the platform and also creating infrastructure. There are application teams. First target will be life science and materials, but we also have other domains, as I'll show you. Other domains also participating in order to see how we drive the science. One thing we need to do is to deal with various modalities, because the science has many types of data. It's not just internet images or text, but rather we have to capture many modalities. For example, in life sciences, we have to capture various omics, from genomics to proteomics. And also have to capture other phenotypes, neural activities in the brain, etc. And we need to correlate them to see what are how some of the functions, some of the omics would affect the other places in this omics hierarchy. So how to capture data? Well, RIKEN has the ability to capture this data or to simulate these data, but we also have to be much more efficient and streamline and standardize. And of course, we have to create models and apply them to real science to solve hard scientific problems. And for that, we really need to establish a pipeline, scientific pipeline, where we would automate the laboratory experiments. So there's a team working on automated laboratory experiments. Of course, many of the data will become from the virtual space, from digital twins, using large-scale simulations such as those on Fugaku, and this will produce data to train the network, and also which will be used in inference or even for reasoning to achieve scientific results, which will be fed back into new experiments and so forth. There are many challenges, however, and this is one of our team principals, Mohammed Wahib, who will have a presentation tomorrow. And there are many challenges, but also many opportunities. So one thing that's been pointed out recently, and this is also one of the reasons why the so-called reasoning models have become are starting to become real mainstream, rather than people blindingly trying to create ever larger models, but rather trying to be much more smart about it, essentially fusing more classical AI notions such as Monte Carlo tree search with these large language foundation models is the fact that we're running out of data that we can scrape from the internet. So ever larger models not only are too computationally expensive, but also they are not producing results as much as we want in terms of intelligence, improvements to intelligence. But also we are running out of data. So people are starting to really think about how we would handle these. Now, AI for science may offer new opportunities for attaining new sets of data, because as we all know, the scientific data are huge, even compared to those on the internet. So because most of the data on the internet are either repetitive and textual data basically are in the hundreds of trillion, maybe even 100 terabytes, whereas a single scientific data set a single data set can be more than a petabyte. So for example, there are lots of things that are happening with respect to trying to use AI for climate science, so to do weather and climate predictions. But the problem is that the ERA5 dataset, which was collected by ECMWF, amounts to about 8.4 petabytes, which is just too big, because some of the assessment that was done in the work, which we also helped, although we weren't authors, some of Wahib's team helped, in terms of trying to digest the ERA5 dataset to create the weather and climate prediction model. It was the projection was it will take the entirety of Frontier, which is a damn good AI machine itself, not just a HPC machine, but also AI machine, over 8 years. Okay, so this is obviously not feasible. So right now, of course, the research is done by sort of sporadically sampling these data sets. But we need to much more progress to try to be able to digest these huge data sets. And also, it's not just about the size of the data set. Things like very long sequence is a big challenge, because let's say you have a visual transformer, you want to be able to do in-contextual training, but these scientific data sets, again, are huge. So just putting them into the system as a context alone is a challenge, because each of these high-resolution image data sets can be terabytes, whereas like Gemini right now, which is purported to be one of the models with the biggest capability to support these input sequences, only is like 1 million or so. So there's 3 orders of magnitude disparity between the two. So we're working, people at DOE and also people at MEXI, and also people at AST and Hokkaido University, all collaborating, for example, to solve some of these problems. One recent outcome is work where there have been algorithmic advances to allow for these humongous sequence length to be optimized when you try to process the image with a visual transformer by using essentially a classic technique you use in HPC, namely using a spatial subdivision and things like quad trees to basically compress the data and then have make those into input token. And this has allowed processing of ultra-high resolution images at a much greater speed as opposed to previously, and also improve the accuracy. So innovations like this, which will not happen on the internet because most images are like 2,000, just HD, which is like 2,000 by 1,000, or even 4K, but not 100,000 by 100,000. So we need to make these advances. And then the consequence of this is we have those capabilities, we can do breakthrough science. So this is essentially what the team, as application to this, the teams are trying to do, is to essentially achieve brain uploading by being able to use the same technology to be able to capture the structure of the brain, because now we have tactography scan capability to do micron level recovery of the structure of the human brain. But then you can use all the image analysis using, again, like visual transformers to do segmentation and reconstruct the connectomes in the brain, or the synaptic connections in the brain. And then, of course, Fugaku has the ability to do full-scale brain stimulation, even up to humans. And we have abilities to do various types of data assimilation by doing brain scanning in real time and assimilating with the simulation to fine-tune the parameters to the extent that we, maybe not so much tune you in the future. They'll start with the mouse brain. But being able to capture, non-intrusively capture the structure of the brain and then upload it into the cyberspace to simulate it, which is what the science fiction movies tend to do. Right? But now it could become a reality. Okay, also things like manufacturing. So we will have new Nikui, Koji Nishiguchi, who's a professor at Nagoya University. Also working with our team lead, one of our team principals, Tsubokura-san, who did the COVID work, but they're into manufacturing. So how do you come up with generative AI to come up to produce parts, very complicated parts with very complicated geometry to be used in advanced manufacturing situations like GigaPress? So there are there's lots of good work on image generation and movie generation. But 3D generative AI, such as like Sora and so forth, they don't really produce real. There's no guarantee that they'll produce something that conforms to physics. Now, there are a lot of work now to do this, but what they're doing is concentrating on like automotive parts that should be manufactured. So they have various things. They're doing various things to incorporate structural dynamics into this generative AI, such that what will be generated will be very likely to be physically conformant to real physics, and also be optimized to the external parameters from day one. Of course, there are lots of challenges because there are various types of structures, like various thing manifolds, and the interaction between parts. But they're working on this. And if you couple this with language models, they predict that human feedback can be done by non-experts, and this will directly turn into design and manufacturing of parts that are necessary to achieve the both aesthetics, but also the mechanical requirements that are posed by non-experts. So having non-experts participate, just as now we can prompt to create movies, they hope that just by prompting and conversing with the AI, we can generate, we can actually manufacture mechanical artifacts. So that'll be a fantastic innovation. So we are trying to augment Fugaku with the new sets of machines in 25. This will be an AI machine, a machine that's tailored for AI. This will be a GPU cluster. In fact, we'll have two GPU clusters, one for this and one for the quantum. This will allow us to greatly enhance the AI capability. It'll be a machine with several thousand GPUs, but will be tightly coupled Fugaku and the storage system and with very high bandwidth optical interconnect. But we're right now going on the procurement for this machine. But one thing we found that when you go through a procurement, you really have to have benchmarks. So benchmarking large language models, especially for AI for science, and also other types of AI models for AI for science, is not established. So that's another thing we're collaborating with DOE in the DOE-MEXT alliance to come up with very effective benchmarking of AI workloads, especially those focused in science. For quantum, switch gears to quantum. There'll be a lot of quantum talks at this symposium, but essentially what we're doing from an infrastructural point of view and system point of view is to try to create a quantum HPC hybrid environment which will host multiple quantum machines and multiple supercomputers and software stack to be able to allow our quantum applications and algorithm developers to create a software that would be that can be transportable across different machines, both quantum and classical. So we're connecting, we're acquiring IBM System 2, IonQ System 2. We're also acquiring IonTrap, which is a Quantinuum machine. We will also try to integrate some of RIKEN's RQC machine. And we may have other partners as we go along. And of course, we'll try to couple supercomputers, not just Fugaku and the new GPU system, but we also try to couple the supercomputers from our partner institutions such as University of Tokyo and Osaka University to create this comprehensive distributed quantum HPC platform. But of course, the real meat will be in the software and algorithms. So it's one thing to connect them by networks, but you got to have the software, you got to have the algorithms. So that's what the new project working on, led by Ms. Sato. But again, there will be many talks. For example, talk by Miyako Tsuji, one of our unit leaders. And so the project is underway. So if you come to the R-CCS building, you'll see a room, which is not yet, and which is complete now, which will look like that, except you won't see the machine yet. This will come in a few months, unfortunately, so we don't have the machine yet. But you'll see this very science fiction-y like white room right near our lobby, and this is where the IBM machine will be. The Quantinuum machine is being facilitated in Waco, and this is something we can't see today. But this is being handled by our experts, who are experts in lasers, because these machines are controlled mostly by lasers. So we have experts in laser optics who will be facilitating this machine. There are already good results in quantum. This is in collaboration with IBM, within our team led by Seiji Inoki, where I won't go into details, but for the first time, coupled significant qubits in a quantum system, up to 77 qubits, and significant HPC resource, which is 6,400 nodes on Fugaku, to essentially solve a real problem, albeit with approximation, to solve some of the material science problem, which is sulfuric compound, and analyzing a sulfuric compound. Now, so this is important because more traditionally in these types of hybrid computing, such as those involving variation algorithms, the quantum machine may be doing most of the heavy lifting, but the classical part was lightweight because I was doing optimization over a very small network. So most of the quantum classical fusions were not quantum HPC. But this time it is, for the first time. And also this time it solved a problem which would have been very difficult to solve on Fugaku, even though there's still a bit of approximation. So this is what you might call one of the first demonstrations of quantum advantage, not necessarily quantum supremacy, but quantum advantage in what could become a real application. And we're very excited by the results. Okay. Finally, FugakuNEXT, if you spare me 5 minutes, there are many things we're doing. And as we presented last year, this involves collaborations for the first time with not just vendors from Japan, but vendors from the US, from the United States, and maybe you can call it UK. Or you can call ARM UK or US or Japanese company, depending on how you look at it. But basically, international coalition of vendors were involved. Not just and of course, we had the teams from R-CCS and also our partner institutions within the high-performance computing infrastructure centers and our application partners. So the big change is, unlike when we did the Fugaku, which was a 10-year cadence from beginning to the end, we are now preparing to be much more sustainable, in that we will be conducting research and development of FugakuNEXT, as you see in the middle of this bar. And we just announced that we will be doing this yesterday. There was a press release that said we will be doing FugakuNEXT development. But also with more like a 5-year cadence, where we'll be overlapping the operation of Fugaku, and of course we're doing improvements in order to achieve that, as what I said in the first part of my talk. And we'll be doing FugakuNEXT development, but also we will be doing FugakuNEXT, whatever that can be called, feasibility study. And we will be likely be doing this not just with ourselves, but also in collaboration with our international partners. So thus, we created this new division, Next Generation HPC Infrastructure Development Division, and this will be led by Masaki Kondo, who was also a leader of a feasibility study. And we have several units and a management office. But the intent is not to confine the development and research involving the next generation systems, but have them be the axis where research teams with all of R-CCS and our partner institutions will be involved, including, of course, the labs, universities, but also the companies. So it's not, unlike Fugaku, where its development was largely confined within this development office, we will be very open, we'll be very forward-looking and involving many research and development that the teams and our partners will be involved. That'll be a huge change. And that's why we had to have a dedicated management office to do this. So we have some, we are issuing the RFP. In fact, the RFP may go out today or tomorrow with regards to the initial design of Fugaku. And we've been doing this feasibility study for the past couple of years, 2.5 years. And we got the straw man system straw mans from proposals from multiple vendors, and we have analyzed them and tried to come up with a unified requirement. And of course, this is still very tentative, but we asked the vendors to try to respond to, not necessarily maybe satisfying, but or even going over, are these numbers. So we would achieve close to order of magnitude performance gain in terms of raw hardware performance for traditional HPC applications, but also to achieve near what could be called Zettascale performance in AI, but still try to keep the power consumption to be below 40 megawatts, and that'll be a huge challenge. But the results from the feasibility study seem to indicate so. But of course, we'll try to refine this over the next year when procurement's over. We will designate our R&D partner, officially designate our official R&D industrial partner, and we'll have the new office ready, and we'll steam ahead with our development, the first year development plan in 2025. I don't have time to go into all the details. There were lots of technical stuff that I was going to cover, but we ran out of time, like doing all the analysis and what we're thinking. But if you're interested, look at the slides. There are lots of interesting stuff that we're thinking, like the use of more emulated FP64, thinking about various interconnect, which the traditional school of thought was like compute-bound apps like DFT with dense linear algebra and thus have correlational impact. Memory-bound apps such as sparse linear algebra kernels, so correlation with like HPC and Graph 500, so bandwidth and memory and network may matter. But we're thinking completely off. This is no longer true, right? For very good reason. And I was going to go over why that's so, but if you're interested, please look at it. But in a nutshell, we think that what's been done in AI, involving scale-up, combination of scale-up and scale-out networks. That a scale-up network is a high bandwidth localized network, extremely high bandwidth, but confined within a pod or something like a few hundred processors, and then interconnect them using a scaling, but however lower bandwidth, lower bisection bandwidth, fairly high injection, but low bisection bandwidth network, such as you might see in things like NVLink plus InfiniBand, or it can be combined using something over Ethernet, would be the right choice. So we have qualitative assessment to think this will be so. But we will be doing first here, this will be one of the works, to try to assess the quantitative aspects of this to prove over many applications this will be the right solution, and the network like Tofu D will be outdated, will not be the choice. Okay, and we're looking at AI workloads and what are the necessary things, what are the necessary topologies, algorithms. So we'll be doing a whole bunch of stuff. So finally, towards Zettascale. So simulation workloads, hopefully raw performance gain. We'd say 5x to 10x. Hopefully we can increase that to 10x, 20x, we'll see. Mixed precision or emulation using things like Zettascale scheme or other types of simulation, we can achieve 2x to 8x. We have reasons to believe that with the Zettascale scheme, we can achieve nearly factor of 50 for traditional dense linear algebra application like Zettascale scheme. We can achieve almost up to like 50 exaflops there. Surrogates, or physics-informed neural network, these will also be very essential. So combined, hopefully we can achieve more than order of magnitude speed up over our existing applications. Of course, we're all AI performance, low precision, sparsity, new models, et cetera, et cetera. And then, of course, we're all hardware being able to provide raw Zettascale performance, again, with a 40 megawatt limit, because we want to be very green. And many of these concepts will be tried out in the Aegis AI machine, and to some extent on the quantum machine that will be procured in 25. My final slide. And all of these, hopefully, will be demonstrated next year in 26. We'll have this symposium, but this symposium will be held in a very different environment, where the SC Asia and HPC Asia will join forces, these two conferences being held in winter, and will be held as a big event that we are one of the primary hosts, but also in collaboration with other institutions of HPC Asia, but also with other institutions like NSCC Singapore. That's been traditionally doing SC Asia. And so this will be a big event in Osaka. And we will integrate many of the research exhibitions. Of course, we have exhibits and also referee papers, so it'll be just like ISC or SC. But also we'll try to have tracks where, for example, this symposium will be one of the tracks within this conference. Okay, so make your reservations today if you're interested, or sometime within the next year. And this will be a very exciting event, and we're very excited to try to establish. This will only be a single event, but hopefully, over the next several years, we can establish Asia Pacific as one of the third axis of HPC and AI, as has been for by wonderful conferences like SC and ISC. But this conference hopefully will continue this convergence in the future to be the third event where all the stakeholders, vendors, and there will be tons of participants that will be demonstrating their latest and greatest in HPC and AI. Okay, with that, I'd like to end my talk. Thank you very much.